Picture this. You're 35,000 feet above the ocean. The temperature outside your window has dropped to almost -50 degrees, and somewhere beneath your armrest, tens of thousands of liters of jet fuel are quietly keeping you alive. Most passengers assume that fuel is tucked away somewhere safe, deep in the belly of the plane, or hidden in the tail. But that's not where it lives. The truth is stranger, and honestly, a little unsettling. Almost all of that fuel is sitting inside the wings, just a few meters from two engines that burn at over 1,000 degrees. It sounds like the worst possible place to store something this flammable, and yet, aviation engineers will tell you it's actually the safest, smartest decision in the entire aircraft. Today, we're going to break down exactly why. You'll learn how fuel secretly holds the wings together at 900 kilometers an hour, why an empty wing is actually more dangerous than a full one, and how airlines turn a literal firebomb into one of the safest components on the plane. By the end, you'll never look at a wing the same way again. This isn't a surface-level explainer either. We dug through decades of aircraft design history and real engineering principles that most aviation channels never bother explaining in plain language. So let's start at the beginning, because it took engineers almost 30 years of trial, error, and a few very bad ideas to figure this out. In the earliest days of flight, nobody even considered putting fuel inside a wing, because there was barely a wing to speak of. The first aircraft were built from thin wooden struts and stretched fabric, and their wings were so flat and so fragile that you couldn't have fit a bottle of water inside them, let alone a fuel tank. So early designers did the simplest thing they could think of. They bolted a small metal can right above the pilot's head, or strapped it directly onto the engine. It worked, because gravity did all the work. Fuel simply dripped down into the engine, the same way water pours out of an upside-down bottle. Pilots liked it too, because they could literally watch their fuel supply shrink in front of their eyes and know exactly when it was time to land. But those flights were short. The tiny canisters ran dry fast, and their bulky shape dragged through the air and slowed the whole aircraft down. As planes were asked to fly further, engineers strapped bigger tanks under the belly or bolted them to the sides, and the results were clumsy, heavy, and aerodynamically ugly. Everything changed in the 1930s, when aviation made the leap from wood and fabric to solid metal. Aircraft like the early metal airliners that would eventually lead to legends such as the DC-3 needed to support heavier engines, longer routes, and dozens of passengers, so wings suddenly had to be built thick and strong. And that's when someone noticed something interesting. These new metal wings had a huge amount of empty, unused space inside them. The idea of filling that space with fuel seemed almost reckless at first. How do you keep a liquid contained inside a structure without it leaking out of every seam and rivet? Engineers first tried fitting rubber bladders inside the wing, essentially giant hot water bottles bolted into the frame. It stopped the leaks, but the bladders were heavy and wasted precious space. Eventually, manufacturers figured out how to seal the wing itself so tightly that the metal skin became the tank. Every rivet and joint was sealed with special compounds, and the wing simply became a container. The moment fuel moved into the wings, planes instantly got faster and more efficient, because all that external bulk disappeared. But engineers noticed something strange almost immediately. A wing full of fuel flew smooth and steady. The same wing, once it emptied out, started shaking noticeably more. That tiny detail turned out to be the first clue to a much bigger secret, one that had almost nothing to do with simply feeding the engines. Have you ever stopped to think about how little spare room actually exists inside a commercial airliner? Every single centimeter of that fuselage is fought over. The main body of the plane is the most expensive real estate on the entire aircraft. Its job is to be a sealed, pressurized capsule that keeps hundreds of people warm, breathing, and alive at altitude. Would you really want to sacrifice that space to store giant tanks of liquid? If fuel had to live in the center of the fuselage, airlines would have to rip out dozens of seats or give up cargo space entirely. And there's more hiding under the floor you walk across to reach your seat than you probably realize. Kilometers of cabling, air conditioning ducts, flight control cables, and cargo holds packed with suitcases and mail. Now add the fuel itself. A single liter of jet fuel weighs almost 800 grams, and a long-haul aircraft can carry well over 100 tons of it. Concentrate that much weight into one single point in the fuselage, and you create a structural nightmare. An enormous, unbalanced load the frame was never designed to hold in one place. Storing fuel in the wings solves a second, much less obvious problem too. Have you ever caught a strong whiff of jet fuel while waiting at the gate? If those tanks sat inside the cabin, that sharp chemical smell would eventually seep through every seal and vent straight into the air you breathe. By moving fuel out into the wings, engineers physically separated that odor source from the living space of the aircraft, keeping the cabin air cleaner for hours-long flights. But this weight sitting beneath your feet during boarding isn't just being stored out of convenience. Clearing the fuselage of that mass gave engineers room to fit in complex avionics and crew rest areas instead. The wing stopped being just a surface that pushes against the air and became something closer to a perfectly engineered warehouse, external, incredibly strong, and able to spread weight evenly across the whole aircraft. But what happens to that careful balance once the fuel actually starts running out mid-flight? Have you ever wondered how something this massive manages to stay level in the sky without tipping onto its tail or nosediving on takeoff? The secret is balance, and fuel in the wings is doing most of the heavy lifting, literally. Think of a playground seesaw. For it to sit level, weight has to be distributed evenly on both sides. An airplane works on exactly the same principle. If all the fuel sat in one giant tank at the nose or the tail, even a small shift in fuel level would force pilots to constantly fight the controls just to stay level. By placing fuel out in the wings, engineers put the heaviest single load right at the structural center of the aircraft, close to where the plane naturally wants to balance. But keeping that balance while fuel is constantly being burned off is its own challenge. A long-haul aircraft can weigh dozens of tons more at takeoff than it does right before landing. So how does the plane stay steady as that mass disappears, gallon by gallon, engine by engine? This is where a quietly brilliant transfer system comes in. Fuel inside the wings is split across multiple separate tanks, and dedicated pumps constantly monitor the levels on the left and the right, making sure both sides stay perfectly even. It functions almost like an invisible scale, shifting tiny amounts of weight back and forth in real time so the aircraft never tips to one side, even in a hard turn. And what happens if that balancing system ever fails? Even a small imbalance between the left and right wing can turn a routine flight into a fight against the controls. The aircraft will start pulling to one side, forcing the autopilot to burn extra energy, correcting the drift. That's exactly why fuel is never burned randomly. Tanks empty in a strict, pre-programmed sequence, one after another, specifically to keep the center of gravity locked in place the entire flight. On some long-range aircraft, engineers even go a step further, using small tanks in the tail to fine-tune the balance point during cruise for better fuel efficiency. It sounds almost unbelievable, but a handful of grams of fuel shifted between tanks can measurably change how hard the engines have to work to keep the nose level, which is exactly why this transfer system runs quietly in the background throughout the entire flight, adjusting itself long before a pilot would ever notice anything was off. All of this happens so the aircraft can fly smoothly and predictably no matter how much fuel is left in the tanks. There's another benefit too. Heavy, fuel-filled wings are naturally more resistant to the weather's worst mood swings. When a sudden crosswind hits the aircraft, those loaded wings behave like heavy pendulums, refusing to swing wildly the way an empty, lightweight wing would. But that raises an uncomfortable question. If wind and turbulence are constantly pushing and bending these wings, why don't they simply snap under all that stress? If you've ever looked out the window mid-flight, you may have noticed the wingtips flexing gently upward, almost like the wings of a massive bird stretching mid-flap. In that moment, enormous forces are fighting each other across that thin metal structure. Air is pushing up on the wing with tremendous force, trying to lift the entire multi-ton fuselage into the sky, while the weight of the cabin, passengers and cargo is pulling the whole structure down. Engineers call this a bending moment, but in plain terms, the wing becomes a long lever and nature is constantly trying to snap it, right at the point where it joins the fuselage. Can you imagine the stress running through the bolts and joints, holding that connection together? This is where the most counterintuitive secret of the whole aircraft hides. Logic tells you that to make a wing lighter and safer, you should strip out as much weight as possible. Aircraft designers did the exact opposite. They deliberately loaded the wings with tons of heavy fuel. Why would anyone add extra weight to a structure that's already under this much strain? The answer is surprisingly elegant. When fuel sits out in the wing, its weight pulls downward, working directly against the lift, trying to push the wing up. It's a tug-of-war happening inside the metal itself. Air pushes the wing skyward, fuel pulls it back down, and the net stress on the joint where wing meets fuselage drops dramatically. Think about carrying a long pole balanced across your shoulders. If you hang a bucket of water off each end, the pole bows gently downward, and suddenly it's far easier to keep steady and centered than an empty pole whipping around in the wind. Now imagine the opposite scenario, fuel stored inside a heavy fuselage while the wings stay completely empty. On takeoff, that sudden burst of lift would yank on empty, lightweight wings so violently they could fold like an umbrella caught in a storm. By filling the wings with liquid mass, engineers made the fuel's own weight work in the aircraft's favor, quietly fighting to keep the whole structure straight and intact. But here's a question that sounds even scarier. If a wing is this flexible and constantly under conflicting stress, why doesn't metal fatigue eventually tear it apart? After all, aircraft are constantly slamming into invisible pockets of turbulence, and every one of those hits is a small blow to the structure. You've probably noticed a low hum and gentle shaking during a flight and assumed it was just the engines working. But pilots and engineers are watching for something far more serious. There's a term in aviation that makes even seasoned professionals treat a wing with real caution: flutter. Picture a sheet of paper hanging out the window of a moving car. At a certain speed, it stops sitting calmly in the airflow and starts violently whipping and snapping back and forth. A wing can behave the same way. If a lightweight structure starts resonating with the airflow hitting it, the vibrations can build on themselves and grow stronger with every cycle, powerful enough to tear solid aircraft-grade aluminum apart in seconds. So how does 100 tons of jet fuel help prevent something like that? The answer comes down to simple mass and inertia. Try shaking an empty plastic bottle quickly in your hand. It's effortless. Now try doing the same thing with a bottle completely filled with water. The liquid inside resists sudden, sharp movement. It's heavy, it's sluggish, and it fights back against fast changes in direction. Fuel inside a wing behaves almost identically. When turbulence or a sudden gust tries to set the wing shaking, that huge mass of liquid resists the motion, absorbing the energy of every jolt and turning what could be a dangerous vibration into a barely noticeable wobble. Engineers actually calculate fuel weight and placement with this exact effect in mind. Inside real fuel tanks, internal baffles with strategic openings do more than stop fuel from sloshing violently side to side. They force it to move slowly, soaking up the energy of every bump along the way, similar to how a hydraulic door closer keeps a heavy door from slamming shut. Without that liquid mass, wings would be far more vulnerable to fatigue, with every invisible pocket of rough air chipping away microscopic damage that could eventually add up to real structural danger. As long as there's fuel in the tanks, this self-dampening effect keeps working quietly in the background, turning what could have been a serious liability into one of the wing's best defenses. But fuel isn't just a stabilizer, it's also a substance that can ignite from the smallest spark. So why do engineers still insist that storing it out in the wings, this far from the cabin, is actually the safer choice? Have you ever wondered why, in a hard emergency landing, people sometimes describe the aircraft as basically a giant tank on wheels? It sounds terrifying, but the placement of fuel in the wings is actually one of the most carefully considered safety decisions in the entire design. Imagine for a moment if all that fuel sat directly beneath your seat inside the fuselage. In any serious structural failure, passengers would essentially be trapped inside a massive fire. By pushing fuel out into the wings, engineers created the maximum possible distance between passengers and that dangerous load, distance that buys precious seconds and minutes, and in aviation, those seconds decide outcomes. But how do you stop tons of liquid from turning into a fireball on impact? Wings are actually engineered to behave predictably in a crash. If an impact is severe enough, the wing is designed to shear away at a specific, pre-planned point, carrying most of the remaining fuel away from the passenger cabin as it goes. It works almost like a fuse in an electrical circuit, sacrificing itself to protect everything connected to it. Even if that fuel does ignite, the fire is drawn away from people, giving the crew a real window to evacuate. There's also a quieter, ongoing battle for fire safety happening inside those tanks at every moment of every flight. The real danger isn't usually the liquid fuel itself, it's the vapor that collects in the empty space above it. To stop that vapor from igniting from a stray spark of static electricity or a lightning strike, modern airliners run a clever system that replaces the air above the fuel with something safer. Instead of oxygen, which feeds fire, the space is filled with nitrogen-enriched air, essentially making the environment inside the tank inhospitable to flame. You could drop a lit match in there, and it would simply go out, because there's nothing left for it to burn. This exact system became standard across modern airliners after investigators studying past accidents realized just how dangerous a spark inside an empty, vapor-filled tank could be. And today, it's considered one of the quiet, unglamorous technologies that has made flying dramatically safer than it was a generation ago. There's one more trick worth knowing about. Have you ever spotted a fine mist trailing from the wingtips of a plane in the sky? That's the fuel jettison system in action. An aircraft can't always land safely with a completely full tank. The extra weight puts dangerous stress on the landing gear. So many long-haul aircraft are built with valves and pumps that can dump tons of fuel in a matter of minutes, spraying it into the atmosphere in a fine spray that disperses long before it ever reaches the ground. It's one final safety measure, letting a heavy aircraft become light enough to land safely in an emergency. The next time you glance out at the wing during a flight, you're not just looking at a painted slab of metal. You're looking at the result of nearly a century of trial, failure, and quiet engineering genius. Storing fuel inside the wings was never just a convenient afterthought. It's one of the foundations that modern aviation is built on. That enormous weight sitting beneath your feet is holding the entire structure together, keeping it balanced through wind, turbulence, and thousands of takeoffs and landings. Every part of that hidden system, from tiny transfer pumps to nitrogen-filled tanks, exists for one single purpose: making sure your flight feels completely uneventful. It makes you wonder how many other everyday things are hiding secrets just as clever, right in plain sight. In the world of aviation, the strangest sounding decisions are often the most logical ones once you understand the physics behind them. Turning aircraft fuel into a structural safeguard instead of just an energy source is exactly that kind of decision, precise, deliberate, with absolutely nothing wasted. So next time you feel a little turbulence up in the clouds, remember the tons of fuel sitting quietly in the wings, doing its job, keeping that massive machine steady until you touch down safely. And honestly, that's what makes aviation engineering so fascinating once you actually look closely. The things that seem the most dangerous on the surface are often the exact things keeping you safe underneath it. A wing packed with tons of flammable liquid sounds like a risk. In reality, it's a counterweight, a shock absorber, a fire barrier, and a stabilizer, all built into a single structure, working together every second you're in the air. If this changed the way you look at your next flight, hit subscribe and turn on notifications. There are plenty more hidden engineering secrets like this one still to come.